Lesson 8.7 is about some applications of right triangle trigonometry using the sine, cosine, and tangent functions. Okay, first there's just some basic vocabulary. Let's say that the horizontal line I have drawn here is the ground, and I have an airplane flying above the ground up here, and let's just say I have a person on the ground down here. And if I wanted to draw a sight line from the person up to the airplane and drop a line straight down from the airplane to the ground, forming a right triangle, as I look at this straight on, I would actually match the ground with a horizontal line parallel to it, like so, through the airplane. And looking at this from this angle, from this perspective, these two angles are alternate interior angles of these two parallel lines, and they are therefore equal. And in the drawings that we're going to make to solve the problems that we're going to be solving in this lesson, we're going to be making pictures of right triangles. So we're going to be drawing in right triangles and identifying angles that are inside of them. And what we're going to refer to this angle on the outside as, we're going to call this the angle of depression, because that's the angle that we look down from the airplane at to look at say the person on the ground. And we're going to call this one, say the person on the ground looking up to the airplane, in this case, is called the angle of elevation. And it's just to know that these two are equal because they're alternate interior angles. And the one that's inside the triangle is the one we're going to focus on. So if we're given the angle of depression in a scenario, we know that that's going to be the same measure as this angle down here inside the triangle. So angle of depression and angle of elevation represent the same angle measure. Okay, so let's say that I have a post that I know is 75 feet tall, and I have a wire attached to the ground far away from the post, and I know that that wire has an angle of elevation with the ground of 65 degrees, and I want to know, and it attaches to the top of the post, and I want to know how long is the wire. So with respect to the 65-degree angle, the wire represents the hypotenuse, and the 75 75-foot length post represents the side opposite the 65-degree angle. So opposite and hypotenuse tells me I would use the sine function. And this is basically just a matter of identifying what's the easiest ratio to use based on what I know, based on what I'm given. So I know opposite, and I'm trying to find hypotenuse, and I know the 65-degree angle. So I can use the sine of a 65-degree angle is equal to the opposite side length of 75 over the hypotenuse of the wire, and so I'll call that W. So W times sine of 65 degrees, if I'm solving this algebraically and multiply both sides by W, is equal to 75. So solving for W, W is equal to 75 divided by the sine of a 65-degree angle. Okay, and when I enter that in my calculator, I get W is approximately 83. So in this case, the wire is approximately 83 feet long. Okay, in this next example, let's say that I'm looking sideways. I'm looking a side view of a slope that I'm going to ride my toboggan down. So my toboggan is up here at the top of the hill, and the hill kind of slopes down and all, but if I wanted to, I could kind of figure out a right triangle scenario here. If I come down and I make a right angle like so, and then let's say that, yeah, there's a slope of the hill, but if I look at the average and I kind of take a right triangle through there, I can make a pretty good estimate of how long that run is by, it's going to be approximately the length of the hypotenuse of that right triangle. So let's say that I know that altitude up to the toboggan from the bottom of the hill is 50 meters. So this side here is 50 meters. And I also know that the angle of depression here, that my slope downward is 23 degrees that I'm taking off initially on my toboggan. Well, that tells me that this down here, this angle of elevation down here is also 23 degrees. And I can use that, and I can make x the length of the hypotenuse of this, and solve for approximately how long is my toboggan run. If I start 50 meters up, and my angle of elevation and angle of depression is about 23 degrees. So with respect to the 23 degree angle, I know opposite is 50 over hypotenuse. So I can use the sine ratio. And I could say the sine of a 23 degree angle should be the ratio of 50 over whatever the length of x is, the length of my toboggan run. So x times the sine of 23 degrees should be equal to 50, just using my algebra. So dividing both sides by the sine of 23 degrees, x is equal to 50 over the sine of 23 degrees. And this is, again, a good approximation. So x is about 128 meters. So that's a pretty nice long toboggan run. Okay, in this last example, let's say I've got Rapunzel up in a tower. And so this is a bad drawing of Rapunzel, and she's got her hair, coming down here. And far off in the distance, maybe he's got across a moat, is the prince. And let's say that he is 150 meters away from the base of the tower. And we don't know the length of the tower. Let's call that T. I want to know how long does Rapunzel's hair have to be, for, say, the height from the window down to the ground, for the prince to be able to get up to her to rescue her. So what I do know is that as she looks down at the prince, the angle of depression that she's looking down at is 15 degrees. So that would match the angle of elevation down here, which is 15 degrees, that the prince would be maybe looking up at, or the angle from the ground up to Rapunzel. So I can use trigonometry to find out the height or the length of Rapunzel's hair that it would need to be. So with respect to the 15 degree angle, I want to know the opposite side, and I've got the adjacent 150. So I can use the tangent function. So I can say, well, the tangent of a 15 degree angle should be equal to the ratio of the opposite side, t, over the adjacent side of 150 meters, if I look at this as a right triangle right here. So t is equal to 150 times the tangent of 15 degrees. And I can enter that in my calculator and get that t has to be approximately 40 meters. So Rapunzel's hair has to be about 40 meters long. It's long, very, very long, to get to the bottom so the prince will be able to rescue her. And that's it.